Okay, so hi, hello, yeah. So let me first introduce myself, and then we can start. So this is Introduction to Machine Learning, and I'm a PMRFTA for this course. I'm a PhD scholar in Indian Institute of Science, Bangalore, and today I'll be covering. So what I'm planning to do is that. So I understand that many of you are from different backgrounds. Maybe most of you are not from the computer science background or anything. But what I'm planning to do is that, whatever has been taught in week one, I want to recapitulate it first. And I have some slides through which I can recapitulate the important points that was covered by professor in week one. And in between, if you have any questions, you can ask it then. Or at the end, we can take up final question and answers, any additional questions you might have, right? So if you have any questions related to a topic, just hold on. Maybe I will cover it and then you can ask. Or if I have not covered any topic, you have some additional questions, you can ask it at the end. So like how does that sound? Does it sound okay, or uh, you want any other? Okay, that's okay, right? Okay. Okay. So So if you want to ask any questions, you can ask in the Gmeet chat, or you can join the YouTube live as well. Um, the recorded sessions will be there in YouTube. And yeah, if I see any questions in chat, I will try to answer them. And even if I'm like going through any topic in the slides, you can just stop me and ask me questions there. You can just unmute yourself and ask. Right. So we'll start from very basics. Like I know, like maybe most of you don't have the background, mathematical background, or the even the programming background. So I would say the prerequisites for this course is, you know, uh, till now it is just nothing as such, but it would help if you have some knowledge of, probability and statistics. But yeah, it is not mandatory, but it will help along the way. So if you have some knowledge of prop stats, if you have taken a course, then it's good. Even if you have not, it's okay. Also, a little bit of linear algebra, maybe that would also help in some cases. But yeah, we can do without that as well. Uh, and Yeah, I guess that's it from a mathematical point of view, and from a programming point of view. So the way this course is structured, you don't have to know any programming as such, but uh, ultimately your aim is to uh, use these techniques that you are learning here. And to use these techniques, you have to know a little bit of programming, of course. You need to implement them. And for implementation purpose, I would say Python is required. Okay. And but for week one, I don't think any technical you know details are needed. Uh, these are purely theoretical lectures that, as far as week one is concerned, right? So, any questions on this part for the prerequisites and what what you expect or something, right? Are you good? Yeah. Yes. Right. So, um, do you have any background in programming, like any Python or any other language? Yeah. So, I mean, not much depth, I would say. if you know the basics of, programming, basics of Python, like let's say define a function and, array and, those things. I think you need to learn two packages mostly. Well, there are many packages if you are going into depth, but basic wise, there will be two packages that you need to learn, and those are TensorFlow and Keras, I would say. So, like, you don't need to worry if you haven't heard those names, but they have beautiful documentation, and so mostly what I have seen is that how you can approach if you have not learned those packages is that let's say you are doing some problem using, let's say, linear regression, right? So you can just Google, like, applying linear regression using TensorFlow or Keras, whatever. So they will give you a code, and TensorFlow will have some existing functions which will give you a code in which you can train your linear regression model. You just have to do the parameter tuning. So for example, you will give your, like, let's say, you will give how many features you want to input, or what degree of polynomial you want to use for your linear regression model. Those you have to input, and in the background, TensorFlow will take care of everything else. So if you say linear regression, TensorFlow will know what to do. You give the features input to it. They will have their parameters. On the basis of parameters, you give those inputs, and TensorFlow and Keras will take care of the remaining thing. So yeah, that's the way to go. Yeah, right. Okay, so I can see some questions. Uh, yeah, what kind of important questions can be expected from lectures of week one? So I think in the assignment, I saw some questions which I will cover. Yeah, based on basic linear regression. I don't think in week one linear regression is even covered, but yeah, uh, basic theoretical questions are mostly, I think, in the assignment as far as I saw. And can you help in solving precision and recall questions? Yes, I have one slide in my PPT. I'll go into detail of that. ML deals with exploratory data analysis. Not as such, in this. Uh, so, data analysis is kind of a broad term, to be honest, in which you have, you know, uh, univariate analysis, statistical analysis, and bivariate analysis, and more. It is a more broad thing, and ML is only focused on the techniques on how to build those models. Those, data analysis, I think it's a more broader thing in which you have to do a lot of statistical analysis of the data. You have to understand the data, right? Uh, ML does to an extent, but data analysis is a broader term in which you understand the properties of your data, and then you apply ML, machine learning models to your data to, train and test and, see how the models perform. So I have some questions on the chat. Is it still worth to study TensorFlow because PyTorch is mostly used nowadays? Yeah. So yeah, as I said, TensorFlow and Keras are basic thing. If you know PyTorch, that's even better. Uh, but yeah, that's the way I learned it. Like, I went through TensorFlow and Keras first, and then yeah, now I'm using PyTorch. So yeah, you can do PyTorch. If you can manage with PyTorch, then it's fine. Economics background with slight knowledge in econometrics. Sure, yes, it will help actually. In econometrics, I think it will help. But till linear regression, I think econometrics people have done linear regression. I mean, they have focused mostly on the regression part, but you will get to learn a lot more about different other models, which are not related. I don't know if econometrics guys do decision trees and all this, but yeah, your background knowledge will help. Yes. right. Yeah, I think in the Q&A, some books were mentioned. I don't know if the book you are talking about that was mentioned or not. But if I see in the Q&A, I think some books were definitely mentioned. And like I'm planning to, cover uh, all the books that, like not books exactly, but I will try to give references as and when required. Right. So if whatever topic I'm covering, I will try to give, references if any, and we will see from there. And I think, yeah, although the lectures were recorded, earlier, uh, yeah, I don't know what the following lectures will be, but yeah, I will try to give whatever, you know, references I can give. Hmm. Okay, so yeah, let me start. I think then I can take questions, further questions. Okay. So, yeah. So the basic question is, what is artificial intelligence, machine learning, and deep learning? So, yeah. So if everybody can mute their mics, I think it will be better. But yeah. So I think you might have many people might be confused, like what is the difference between artificial intelligence, machine learning, and deep learning, right? And you have understood. I mean, in week one, you have been given this definition by Tom Mitchell, who first coined the term machine learning, and he said that it is the study of algorithms that improve their performance at some task T with experience E, and this task is a collection of E, T, and E. Like first time I read this definition, it barely made any sense to me. So like, uh, how to explain this, so you are doing some task, you have been given a task. So let's say, for example, the task could be to identify if a mail that you received is a spam or not, right? That's your task. So you receive many spam emails every day in your Gmail ID or whatever. So let's say the task is to identify whether the email is spam or not. And you see the email, and let's say you find some words which you can connect that, okay, if the email has the word money, let's say money 5 times, right? Then you can see that, okay, this might be spam, right? Whereas some friend calling you for lunch, that might not be spam, right? There is no money involved. So you get automatically suspicious when your email, has the word money in it. Are they asking for money from you or whatever? So, you know, so you have that experience, right? So that is your experience, that you can, from your experience, you can tell that, okay, this email contains money. So this email might be spam, and your task is to see whether that email is spam or not. And now you have, let's say, you have received 100 emails, and out of that you have like categorized, let's say, 10 emails as spam, out of which, let's say, two emails were not spam. So two emails you mistakenly categorized as spam. So now you calculate your performance. Okay. So you calculate your performance, and how do you calculate your performance? So this is very subjective. So there is a loss function which I'll come to later on. But here you see that you have categorized two emails which are not spam, but you have categorized them as spam. So that is your performance metric. That so one metric could be, let's say, uh, kind of the false positives. Like what is the false positive ratio? So 2/10. So that is like one fifth, 20% is your uh, false positive ratio. That is your error rate or something like that. Right. So 80% is your performance rate. Right. So now you learn from your experience and you see that whether what are the two emails and why you categorize them as your as spam, which should not be categorized as spam. And now you try to improve your performance with your experience, right? And then you perform the task again, and then you come up with a better model to categorize spam, right? So this is what this three parameters P, T, and E correspond to, right? So okay. Now, yeah, what is the difference between artificial intelligence, machine learning, and deep learning? So artificial intelligence, I would say, is a broad, term again. So artificial intelligence covers everything in which a system can learn from itself. You know, so yeah, I don't have a very objective definition in mind, but anything you see that which can learn from its experience, and produce new results, and that can be classified as artificial intelligence. I'll come to some examples later on in the next slide. I'll come to some examples, of course. But machine learning and deep learning are subsets of artificial intelligence. And in which way are the subsets, and how are they different from each other? That's the question you must be wondering, right? So machine learning is something in which so there are few differences in the machine learning. Okay, so first let's see what are the similarities. Both the systems, both machine learning and deep learning, you give some input, they train on that input, and and then they train on the training data, uh, and then when you put the testing data on that model, they give you the output of that test data. So both the systems work in that way, right? But there are some differences in which machine learning and deep learning works. So machine learning requires some human intervention, whereas deep learning requires minimal human intervention, and they learn on their own. So in which way, where does the human intervention come in machine learning? Is this the experience step, right? So you learn something, right? You learn how to classify it as spam, and then you have to come up with a better model from your experience, and that's where the human intervention comes in. You have to give some better model to the system so that it learns from your experience. Whereas deep learning, it is more, so you have heard about neural networks, right? So how you so okay, I will not go into much detail, but when you give an input to a neural network, and it learns on its own, and it produces the output. There is no uh, human intervention to better to learn from experience. It learns on its own. The experience it learns on its own. Whereas in machine learning, you have to give some human intervention so that the machine learns on its own. Other differences could be, like machine learning has, mm, it trains its model very fast compared to deep learning, whereas deep learning takes a long time to learn. So, this you may or may not have heard about some deep learning models like ResNet and Inception and those things. So if you go into the Keras page, like you can just Google Keras models, Keras deep learning models and something, and it will give you a list of the models which have like millions and millions of data on which they have trained. These are already trained models, right? And they have taken like months and years maybe to train on those data for simple tasks like classification of images, let's say. So if you are given an image, you have to classify it whether this is an image of a cat or a dog or some other animal. And those models, they have already trained those models, and uh, they have taken months, and you give image as input, and it goes through a bunch of hidden layers, and then gets classified as whatever, any animal or something. So those are the things that we do in deep learning. It takes a lot of time, whereas in machine learning, it is not so time consuming. And I think, yeah, I think there might be a few more differences. Does anybody know any other differences between machine learning and deep learning? You can feel free to add. Okay. So, yeah, can you give any example to differentiate linear and logistics regression? Yeah, I'll come to that. I'll come to that. I have some examples on that. Yeah, before I move to the next slide, I'll just, focus on this thing. I think this was covered in week one as well. So in traditional programming, what we do is that you give the data and you write your program and you let the computer do the task and then you get the output. Whereas in machine learning, what you do is you give the data and the output. So by data, I mean, let's say you have 1,000 pictures of cat, dog, and other animals, and you give the output. By output, I mean that all those images are classified as some category. So that is your output. You know that this is a picture of a cat, this is a picture of a dog, this is a picture of a cow, this is a picture of a horse, and so on. And you give the data and the output to the computer, and you let the computer decide, uh, how to make a model of it for, let's say, a neural network through which it passes on, and what are the weights of each of those networks that you have, and so on. Yeah, yeah, I will provide this PPT and the recorded lectures will be available on YouTube. And yeah, any other questions you have? If not, okay, we can move on to the next slide then. Yeah, feel free to join in or add, anything that you feel might be relevant to the rest of the people. And this is a interactive session, so feel free to join or add anything. I guess you guys have different backgrounds, so yeah, feel free to share your experience as well if you have anything in the field. Right? So yeah, we can move on. Okay. So applications of AI. So I mean, these are four applications, but I would say AI is now being applied everywhere. I mean, literally everywhere. I'm not even exaggerating about it, but yeah. So, but here to mention a few of them is healthcare, and to give you some examples, like very simple example, like if you have a disease, now how do you detect whether you have the disease or not? Like, let's say COVID, let's say, which is a pretty recent example. So you have some symptoms, let's say cough and cold, and you have some vomiting or something other symptoms. So you can make a model, like what are the symptoms you have and whether you have COVID or not. So your output is whether you have COVID or not, and your input would be the symptoms that you have. You know, and if you have enough data that like these are the symptoms for a COVID positive person, and these are the symptoms for a COVID negative person. I mean, then we can build a model, and then when a new person comes in, and we can just give his symptoms as an input to the model, and we can just predict whether this person has COVID or not. So this is one basic example. And yeah, anybody else working in this field might share their examples that they have. Okay. Okay. So, finance. Okay. So this is a field which is pretty close to my heart because I have been working in this field. Like I had worked in this field actually for 4 years. And what I used to do is that so I used to work in credit and fraud risk. So what we have to do is that like uh, suppose you are approaching a bank for a loan, for a loan or any credit, any card or anything. So what we used to do is that, we used to get your history, you know, mm, whatever, like your credit history actually, not your personal history, of course, but your credit history, for example, how many bank accounts you have, how many cards you have, how many loans you have existing, and how much debt you have total, and all those things, what is your salary, income, and everything. And based on that, we used to build a model which judges your credit worthiness. So when the bank gives you a loan, they are not give loan to anybody, right? They are going to judge whether you can pay back that loan or not, right? So if you can't pay back their loan, then the bank will be in loss, right? So first they use your credit history, your previous data, your track record, and based on that they build a model, and using that model they give you a risk score, which is basically higher the score, let's say more riskier you are, more there is more probability that you are going to default, you're not going to pay the bank back. So if you have a very high risk score, that means you are going to get rejected. You you're not going to get that loan, right? uh, on the other hand, if you have a lower risk score, you're gonna the bank is going to give you the loan, right? So yeah, that is basically pretty much what we had to do. And another thing is autonomous vehicles, right? So yeah, Tesla, of course, and now I think in India as well, Mahindra and Tata, and everybody is going to the business, and this is pretty much the future actually. You know, so I think in YouTube you can get a video, when you have like that was very old video actually back in the 2000s when the US military was using it was in the very early days of you know machine learning and deep learning, where the US military was using their car to go through a road, and they have a camera attached to the like sort of a dash cam. Uh, can you mute yourself? Okay. Okay. So you sort of have a dash cam which looks to the road, and the AI system that was installed in the car that kind of can has trained itself so that it can distinguish between what is the road and what is the uh, roadside, the grass at the side of the road, or maybe, and it directs the vehicle along the path such that it goes always to the road. And it was showing that that since the system was trained to travel on kind of a one lane road, so when that car was coming into an intersection, or let's say a multiple lane road, it was not able to predict correctly, and it was going off the track, and because the model was not trained on that kind of uh, uh, data. So I think it's a beautiful example on not which shows that you cannot just blindly train your model on any data. You have to make sure that whatever the training data you use to um, uh, model your system, same should be the similar should be the test data as well, right? So yeah, there are some minor such subtleties involved, and which we will learn along the way. Another is NLP. Yeah, of course. So I mean, everybody has heard of Chat GPT and chat bots and uh, all those things. So those are examples of NLP. The NLP stands for, yeah, for those who don't know, NLP stands for natural language processing. So it has to do with how we can interpret language, not just data, raw numbers or something. How we can interpret language, and you know so ChatGPT involves very abstruse kind of models. You require word to vec and transformer kind of things, which are like even I mean, first you have to learn neural networks, and then you have to learn those things. So yeah, if in the future videos, if I get time, I will explain how it works. But yeah, for now, I think, yeah, those are few of the examples. Also, not only NLP, you have must have received some automated phone calls. Those are also, like chatbots, any chatbots. So nowadays, you go into any website and you type in some your query, and the chatbot analyzes your query and gives a response. So those are the examples of NLP. So as the name suggests, natural language processing. So it processes your language, the language we speak, English or any other language we speak, and the system analyzes your language and you know uh, trains a model according to that and gives an appropriate response. Right? So the output is the response in this case. The input is your the user query basically. Yeah, right. So yeah, anybody else wants to add any application? Do you guys work in any field? Yeah, right, right. True, true, true. True. Google search engine, and then like how you rank those websites. I mean, when you search Google, when you search for a query, I mean, most of the time you get at the top what you want, right? You don't have to go into second and third pages. I mean, if you have to go into second and third pages of Google, that means you are probably not getting what you want. So most of the things, uh, Google ranks their websites based on that as well. So there are, yeah, that is a good example of how NLP works in Google. ML in scientific research, yes. I mean, as I said, ML is used everywhere now, in physics, astronomy, biology, everywhere, everywhere. So yeah, I mean, it would take a lot of time to cover all the examples, but if you guys are working in any field where you are using ML, uh, please share your experience. Image segmentation, right? The way, yeah, fraud detection I covered in finance. Yeah, along with credit risk, fraud detection can also be done. Uh, right. Image detection, of course, yeah. Right. Image detection is actually the fundamental basis of neural networks. That's how, I mean, neural networks are mostly used in that image detection. Okay, so let's recommendation system using ML, right? Yeah, movie recommendation. Yeah, even like these e-commerce websites, like Amazon or Flipkart or whatever. They use recommendation system. So you search for some dress on Google or Amazon, whatever. You'll see an ad coming um, whenever you open another website, which recommends you based on the things you have searched or looked up in Amazon and Flipkart. That's a, yeah, recommendation system is a good example. Yeah. Right. So yeah, moving on. Yeah, types of machine learning. Right. As the professor covered in week one, mainly two types of machine learning: supervised learning and unsupervised learning. There is also reinforcement learning, which we'll not cover in this course. But yeah, I mean, reinforcement learning is rarely used in common day life. Maybe if you are you know making a game or something like that, like Deep Blue or something, which can play chess and yeah, yeah. So those request reinforcement learning, but majorly we'll focus on supervised learning and unsupervised learning. So as the professor mentioned, supervised learning is when you have a categorized data set. So by categorized, I mean like, uh, okay. So let's come to the example that I gave earlier. You have some, a set of animals given, and you have been tagged. Those animals are tagged. So you know this is a cat, you know this is a dog, you know this is a horse, and so on. Right. But on the other hand, in unsupervised learning, you're just given some data, you don't know which one is which. You don't have the output parameter, you don't have the y variable, right? So that is when unsupervised learning comes into play. So for example, uh, uh, well, let's see. Okay. Uh, so clustering is one of the examples, which will come back later. But yeah, for example, in supervised learning, I will come to one example each. But if you want to share any example of supervised learning and unsupervised learning, you can just talk about it. But I will go through each of the examples of supervised and unsupervised learning in detail, and I will solve some examples as well. But if you have any example of supervised learning is easy when you have a tag data. So one of the examples that I come to in the next slide is housing prices. So let's say you have a house which is a big house, right? It price will be more, right? So I mean, considering that all other factors remain constant, if you have a bigger house, the price will be more in general. If you have a smaller house, its price will be less. Right. So that is an example of linear regression, right? Uh, so you know what is the price of the house, you know what is the size of the house, and based on that, if a new house comes and you know what is the size, you can predict what is the price of that house. So that is an example of linear regression, which will just come in the next slide. Whereas unsupervised learning is that, let's say you have some houses of different sizes, right? But you don't know like what is the price of each of the house. So let's say there are only small sizes houses and there are only big sized houses, right? And there's no houses in between, no houses of medium sizes, right? So then you can apply clustering and say that okay, this is a cluster of a big sized houses, this is a cluster of a small sized houses. And yeah, now why do we do clustering and those things? Those will again, I'll come to that, and those have some market market strategies. They develop market strategies based on clustering. So if you have one cluster, and based on that you can develop insights on that cluster. So let's say the big sized houses, you can get some feature from that. Okay, big sized houses have these common feature, whereas small sized houses have this common feature. They have, let's say they have um lesser number of rooms, whereas big size houses have a more number of rooms. I mean, this seems obvious, but you can come up with some. In general, we don't have some such obvious insights, but so this is basically just to understand that bigger size houses have bigger number of rooms. So let's say a customer comes to you and he asks that, okay, I have a big family of, let's say, 5 people, and I need at least 3 rooms. So you will not go take that customer to show a small size house. Okay, you'll take that customer to a bigger size house, because by clustering that that bigger size houses have this cluster has larger number of rooms and so on. Right. So those are some of the insights that you can get from clustering and unsupervised learning, so to say. So these are some examples of clustering. Like clustering can be done by k-means, mean shift k-meters. I will not go into details of these because they will covered in the upcoming weeks. And dimensional reduction, PCA, feature selection, linear discriminant analysis. These are some examples of unsupervised learning. So I will not go into detail of each of these algorithms, but I will just say what dimensional reduction is. So let's say you have a data which has 1,000 features. For example, again, come to the housing prices. So price of the house can be determined by size. That is one feature. Second feature could be number of rooms. Third feature is location of the house, whether it's located in a well connected place or is located in a remote place, and so on. There are like 1,000 features, and you cannot plot all those features in your plot and visualize, right? You cannot draw a 1,000 dimensional graph, right? Uh, So what you do is that you reduce the dimensions of the data, and then you see which feature is most important to us. So all the features won't be, equally important to determine the housing price. Let's say size of the house contributes more to determine what is the price of the house, whereas location might not contribute that much. So you reduce the dimension of the data, and then you can also see like which component contributes more to determining the price of the house, and you can also visualize visualize the data uh, better. So that is what dimensional reduction basically means. Again, regression comes in linear. It will be linear regression, logistic regression, decision tree. So I'll talk about linear and logistic regression. What is the difference between them in the next slide? And okay, classification again. It could be naive Bayes, SVM, or KNN. So one difference between regression and classification is that, so let's say the housing price is the best example of regression, where the output is continuous basically, right? The price could be anything, uh, any number basically. Whereas in classification is the earlier example that I talked about is the spam classification, right? Spam classification. There's an example of classification learning, and so where you have like the output variable can only take 0 or 1, positive or negative values. So whether it is a spam, then it's 1. It's not a spam, it's a 0. So yeah, only those two values the output can take. No other values. Right? So that is a classification. Right. So any questions on this example of reinforcement? Yeah. So, yeah. Sorry. Yeah, go ahead. Right. Right. So okay. Let me let me think of an example first. Mm, okay. So let's say you are like a biologist, working in a lab, and you're working on rats. The rats have. So you're considering only whether the rats are obese or not. So your problem statement is to understand whether the rats are obese or not, and what is causing this obesity, right? So you have some data about the rats. So let's say the obesity can be caused by three of the genes that are present in the rat. So you know what is the percentage of gene 1 in each rat, gene 2 in each rat, and gene 3 in each rat, right? So it's a three-dimensional graph, right? So you know what is the percentage of gene 1, you plot this, and gene 2, you plot in the y-axis, gene 3, you plot in the z-axis, right? So now what you do is that, so it's a three-dimensional graph. You cannot draw a three-dimension in a two-dimensional paper, right? I mean, even if let's say you have like in practical cases, you will have many more dimensions actually, not even three. You'll have like thousands or something like that. Let's say. So what you do is that you cannot visualize, right? You cannot like see. I mean, you can plot them in a thousand dimensional data, but you cannot see the graph, right? You can have a thousand dimensional array, but you cannot see which gene is contributing to which what obesity basically, right? That's what you want to know. So what you do is that you reduce the dimension of that data. Again, I will not go into detail like how you do it. That I will do probably when the professor teaches PCA or something. You basically from gene 1 to 100, you reduce to two axes when you have a combination of genes. So in the x-axis, you will have certain combination of genes. So let's say gene 1 plus some factor times gene 2 plus some factor times gene 3 and so on. In the y-axis, you will have again some certain combination of you know all those genes, and then you can you will only have the x and y axis, and then you can plot your where that particular mice stands, right? In the two-dimensional data, right? So from a 100-dimensional data, you have reduced your dimension to Okay, is anybody in? Okay, so if from a 100-dimensional data, is everybody on mute? I think I'm getting some echo. Maybe. Okay, so from a 100-dimensional data, you can reduce it to a two-dimensional data where you can plot, uh, you know, uh, what is the proportion of genes that mice has, you know, and yeah, in that way, also since your axes are a linear combination of the genes, you can also determine like which gene is contributing most to, let's say, obesity or whatever. So that is the a way to visualize your data, and yeah, that is basically dimensional reduction. Is that okay? Or okay, thank you. Okay, any other questions on this slide? Let me check YouTube once. Yeah, the session is still 9. Okay. Yes, I think Himanshu has asked like if your function is f equals to x plus by plus c, then how can you find the cost function for two variables? So yeah, I will come to that in the next slide, right? But in this slide, if anybody has a question, please ask. Okay. Okay. So here, okay, someone has asked example of reinforcement learning. Okay, so as I said, reinforcement learning is something, uh, for example, in games, right? So you're playing a game with someone, uh, let it be chess, okay? So you make your move, the other person makes his move. So you learn from that other person's move, and then you again change your move. You don't have a fixed set of training examples, like you have in machine learning or deep learning. You learn on the go, basically, as the move goes out, and whatever you have learned from your experience, you apply that, and again you look at the move of the other person, and then you make your move again. So you're continuously learning with time, you know. So you are reinforcing your learning, basically, as the name suggests. Okay. So you're continuously learning through time, and you are making your move and playing the game. So that is mostly used in gaming and those kind of stuff. Okay. So this is the example that, yeah, I already introduced you, like housing prices. Okay. So what could be so on the y-axis, okay, this is your what is called the dependent variable, the price. That's what you want to predict. And on the x-axis, you have number of rooms, which is given to you, right? So, like how would you predict the, price given the number of rooms? So you have seen some these examples, right? So the number of rooms of this house is one, and the price is, let's say, something between 180. Number of rooms is two, the price is 190. Number of rooms is three, the price is 200, and so on. You're given these data, right? Now you want to predict like what should be the now, let's say you have trained your model and you are given another example. Let's say the number of rooms in the house is four. So, what should be the price, right? So, you can fit a straight line through these, you know, through the given training set. And when you get this line, from this line, you can predict what is the price of four rooms. So, here it's somewhat around 300, right? Okay. So anything like if you are given a house with 8 rooms, what is the price? You can from this line, right? Now, how we are doing this, So that is the question, right? So like, you can say like, okay, so from looking at this, I mean, this can be done by naked eye, right? We can fit this line, and why do we need a machine? Right? That's the question. So can anybody tell like why do we need a machine to do this? We can do it manually, right? Right. Right. Exactly. So in this example, we only have number of rooms, but the price of a house might depend on the size of the house, the square feet of that house, you know, as I said, the location of the house and so on, and thousands of you know, parameters it might depend on. And you cannot, visualize. The human brain cannot visualize, beyond uh, 2D. Well, some people might visualize 3D, but mostly we cannot plot a graph beyond 2D. So anyway, but again, like we have to understand, like how is the machine doing it even for 1D, and then we can generalize it. Like we can, see how the machine is doing it for n dimensions. Or yeah. So yeah. So uh, as you can see from this flowchart, so first you have to select a machine learning model. So here the model is linear regression, right? Then you set the hyperparameters ranges for grid search. So what do we mean by hyperparameters? So this is a straight line, right? So if you can see, like this is the intercept of the line, 100. This is the slope of the line, 50, right? So these are the parameters. So you don't know these parameters from at the start, right? These are what you calculate, the 150. So you from the start, like uh, you want to fit a line, not a you know curve or something. So let's say you know that you want to fit a line. This is a one dimensional linear plot, but it might not be. So I will come to that. If what if I consider like let's say another parameter, let's say number of rooms square, the square of the number of rooms. So what will happen then? So and then you do cross validation. I think the professor again has covered cross validation, and then you tune the hyperparameters and then finally evaluate your results, right? So yeah, I mean, what these exactly mean, I'll just explain in my notepad. So let me just come to my notepad. Okay, so on this axis you have given price, on this axis you have given number of rooms, right? So these are the examples that you have been given. So let's say you are fitting this line. Okay, this is the line you want to fit. Now, you want to ask yourself, like, what is the error if I fit this line? So the error you calculate as summation of all the examples that you have. Okay, minute. Yeah, y hat minus yi whole square. So y hat is the predicted, sorry, predicted value of price. Yi is the given or observed value of price. So these black dots are what you observe, right? So this is the value what you observe. This value, let's say 200. This is 100. So this is the observed value, right? And then let's say 300, 400. And what is the predicted value that your model is capturing here? So these are the predicted value. So for this is the predicted value, this thing. For this is the predicted value, this is the predicted value, and so on. So now, what we are doing here is calculating the difference between the observed and the predicted value. So you're basically calculating you know, this distance, squaring it, and adding it to the square of this distance, adding it to the square of this distance, adding it to the square of this distance. Okay. So that's why the summation is there at the beginning. So you are squaring the, well, this is called the least square distance. Okay. That's the name that you have. And this is the least square error basically. Okay. So if you see, these lines are, very long, but if if you can fit a line like this, the mean square distance is automatically, minimized, right? So that's why you would choose this line and not the other one, right? Again, what is the y hat here? So if you like write it algebraically, y hat here is basically a plus bx, where x is the basically the number of rooms you have. And then you have to predict what is A and what is B, right? And how do you do that? You do that by minimizing this error. And how do you minimize this error? You minimize this error by doing gradient descent. So, yeah, someone has raised a hand. Can you ask? Yeah, you can ask question if you want. Ronak. Yeah, yeah, right. Yeah, if you say, I mean, if you mean by hat, you mean the predicted parameters? Yeah, that's it. Right. So, gradient descent algorithm is, I think, is not covered in week one. It will probably be covered in week two. So, I'll not go into it right now. Maybe in the next week, I'll go into it when the professor has already covered it. But if you have any questions in that, you can ask me. But if not, I can move on. Is everybody able to see what I'm presenting, right? In the notepad, I can make it bigger. If you want. Right. Now, yeah, now what if, you have number of rooms? What if you have like another variable? Let's say, you know, number of, let's say the size of the house, right? Wait a minute. Okay, this variable, I guess. Okay, yeah. So on this axis, you have number of rooms. On this axis, you have the size of the house, and you're trying to predict the price. So this is a 3D graph. It's hard to visualize, but anyway, I'll try. So if you have, let's say you have size for a particular size for a particular number of rooms, you have the price here, and for another set of pairs, you have here, and so on. So you're populating points in a 3D space, right? It's very difficult to visualize. So this is what I'm talking about when I said about dimensionality reduction. Right? But even if you don't visualize it, we can just do it algebraically. Let's say, so what is basically we have to do here? Your y predicted will become a plus bx, let's say x1 and c x2. Right? So x1 is your number of rooms, x2 is your number of sorry size of the house. Okay. I don't quite- Let me just fix the size here. Everybody can see the notepad, right? I mean, the letters are not too small, right? Okay, that's it's visible, right? Okay, someone has asked what is gradient descent? Explain in brief. Yeah, I will do that. I will do that. So, now your y predicted has changed, right? So, what you do is, your error will now be summation of over all the examples a hat plus b hat x1 plus c hat x2 minus the y observed yi whole square, right? And you want to minimize this error, right? So gradient descent is basically nothing but a process to minimize an error and determining what is the A, what is B, and what is C when your error is minimal, right? So the best fit line, uh, what is basically the best fit line, right? So, I mean, i- if you are familiar with calculus, you must know that, what do we do if you have to like find the minimum of a function? So this error, this is a function, right? This is some j of, you know, function of a, b, and c, right? This is the error function j. So can anybody tell me like how do you minimize a function? Right, 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 exactly. So what we'll do is that, yeah, we'll do differentiation of this function. Right. So we'll do dj with respect to a, right? And we'll see, we'll equate to 0, and we'll see what is the value of a we are getting. Similarly, we'll do dj with respect to b equals to 0, and we'll see what is the value of b we are getting, right? And so on. And we'll do it for uh, any number of parameters that we have. Right. So that is the basically the method, and then we will iterate over, you know, A, B, and C until we get the best fit line. Right. So that is basically gradient descent. I think it has been covered in week uh, 2, and maybe if you still have some doubts, I can do it in the next week. Right? So right now, I think we should move on, and so this is an example of linear regression. I hope everybody has understood it. If you have any questions, you can ask me now. Yeah, yeah, sure. You'll get the recorded session. You'll get the recorded session. You'll get the notes. You'll get the PPTs. Yeah. Um, yeah, it's in my name. Um, uh, so what you'll get is you will get the YouTube link of the video that you'll get. NPTEL will provide it to you. I'll provide to NPTEL, and yeah, it will provide you through mail. They will. Uh, okay, I can do that as well. Yeah, okay, I will do that. So, Yes, I'm coming to that. Okay, so yeah, this is the link for the channel, and yeah, as yeah, I guess someone has already posted the link for the video as well. Okay. Okay, so yeah, someone asked what is the difference between logistic and linear regression. So exactly, I guess that's what I have in the next slide. Okay, so this is an example of, so you already saw what is a linear regression. The last example was a example of linear regression, right? And now you will see like what is a logistic regression. So I guess I have covered this example. Like I've talked about this example earlier on, like um, classifying an email as spam. You have thousands of emails, you want to classify them as spam, and you want to know like whether that email is spam or not. And yeah, so that is basically the algorithm you know uh, where you need logistic regression. Like, but the question is again like, how do you do it, right? So again, I'll go back to my whiteboard. So before that, I just want to explain one thing. Okay. So in this picture, if you see, so the hollow circles that you see are basically not spam, whereas the solid circles are basically spam. Okay. So now, what is your model? Your model is classifying whatever is within this region, with this circular region. The model is classifying everything as spam. Okay. So in this region, if you see this green region, these are the examples which are solid circles. That means they are actually spam, and your model is also classifying them as spam. So these are called true positives, because they are truly spam. Sorry, they are because they are like positive examples, and your model is characterizing them as true. Okay. Whereas in the this red region, these are called false positives because they are positive examples, like positive, not positive examples. They are like being positively classified as spam, but they are actually false. They are actually not spam. You see, these are hollow circles, so they are not spam, but they are falsely classified as spam. So that means they are called false positives, right? Whereas in this region, these are spam, but not classified as spam. So they are called um, you know uh, false negatives. Okay. And on the other hand, sorry, false positives. Sorry. Yeah. So they are truly they are. Wait a minute. Am I mistaking something? Okay. So the green region is the true positives. The red region is the um, false positives. and this region is the false negatives, and this region is the true negatives, right? Okay. So again, if you see from this chart, okay, so the true class is positive. So by positive I mean spam. So if they are truly spam and your predicted class, if you are classifying as spam, then it is true positive. So the green region. On the other hand, if the true class is negative, but you are still classifying them as positive, if you are still classifying them as spam, even though they are not spam, then it is false positive. So the red region. So again, if the true class is positive, that is truly they are spam, and you're classifying them as not spam. So this region, the dark gray shaded region, that are false negatives. Whereas in the light gray shaded region, they are not spams, but and you are also not classifying them as spam, so they are true negatives, right? So this way, this graph is a way to think about it. I think otherwise it's very confusing actually. But yeah, this is how it works. Someone has talked about definition of recall and precision. Yeah, I'll come to that in a moment. Before that, I just want to explain like how do I mean, I'll not go into detail, but you know, just to see like uh, how you classify them as spam or not. Yeah, on which factors we can determine the email as spam or not. Yeah, I'll just go to that. Right. So let me see. Okay, I think it is visible now. Okay, so yeah, you can see it here, right? Mhm. Okay. Okay, so let's say, as I was mentioning earlier, like at the beginning, so if you have some on what factors we can determine spam. So, uh, I mean, the modern day spam algorithms that we have is that, so if you're, so you might see that, when you receive a lot of mails, once you classify one mail as spam, you won't get similar mails next time, right? So your machine trains its model based on, so you are giving the tag to the model. You are saying that, okay, this email is tagged as one, should be tagged as one. So that's where the machine gets the output, right? The output Y parameter. That's where it gets it. And whereas how it gets the input parameters. So the machine looks for words in that email. So let's say you classify one email as spam, which says money, money, let's say 5 times money. Okay. And you classify this email as spam. So now the machine learns from this email. So this is tagged as one. Whereas another email which is sent by some of your friend, maybe he wants to meet you for lunch, this is not tagged as spam. So this is the Y variable, the output parameter, right? Whereas this is the X variables, the input parameters that you have, right? So the machine has both the X and the Y variables. Now it builds a model based on, so there are like thousands of emails, so on, right? And all are tagged as such. And the machine uses, uh, well, there are a lot of complicated steps in between, like how to convert words into numbers and so on. I'll not go into the detail of those, but this is basically the outline which the machine does. It looks into each of the emails and it sees that whether how many times money has, like the word money has in this email, and if it has some, you know, uh, let's say money was mentioned twice in the email, it will have a certain probability of getting into spam, and it exceeds certain threshold, then the machine automatically puts it into spam. So that's how does it. And again, as someone mentioned, like what is the difference between uh, logistic regression and Linear regression. In linear regression, you saw that your all the values it was taking was a continuous values, whereas the output values. Whereas in this case, the output values are discrete values. Like it can be spam or not spam. It can be one or zero. Like right, it cannot be like 100. Right? What does 100 mean? It means nothing. So it can either be yes or no, yes spam, no spam, one or zero, positive, negative, whatever you call it. Right? It can only take binary values. So that is the difference between basically logistic and linear regression. Rest of the method, uh, is same. I would say in both the processes. So, like as we saw in linear regression, what we do is we calculate an error function. In this case, also we calculate an error function. The error function is no longer the least square. We do something called the entropy function. I think you might have heard, or maybe you will hear it when the professor teaches about logistic regression. And then we used gradient descent to, get into the least error, the least entropy solution. And from there, we can get the parameters, right? So let's say your model has trained and it has trained like spam equals to, you know, if money is mentioned like one time, it will get a weight of let's say zero point 0.5, and if lunch is mentioned one time, it will get a weight of 0.01 because it has less weight, less probability of becoming a spam, and so on. This is a very crude model. Okay, this is not exactly how it works, but yeah, just to give you an idea. So these again, these are the parameters which get trained. Let's say this is a hat corresponding to what we got in logistic regression. This is a B hat, and these are the parameters that uh, it obtained from by minimizing the error. Right? Okay. So, uh, is there any other questions? So, yeah, someone has asked what is precision and recall. I'll just go into that. If you have any other questions, you can ask me right now. Okay. So, uh, what is the accuracy of our model, right? So, firstly, accuracy is number of true positives plus number of true negatives divided by total samples. Why true positive by plus true negatives? Because these are the samples. The true positives are the ones which you have, uh, you know, which you have correctly uh, tagged. Whereas true negatives are also the ones which you have correctly tagged as negative. Whereas false positives and false negatives are the ones which you have incorrectly tagged. Right. So that's why this is the accuracy. So accuracy is basically the correctly tagged uh, set divided by the incorrectly tagged set. So you can directly calculate from this example, like what is the accuracy of the model. Like you can count the number of true positives, the number of true negatives, and find what is the uh, also the total sums. I think it's countable, right? It's not many, and you will count what is the accuracy. So can someone like count it and just tell me what is the value of accuracy in this example? While I take a 2-minute break, maybe I just come back and maybe somebody can tell me what is the accuracy. Okay. Okay, did anybody calculate what is the accuracy? 0.54, 54%, right? Okay. So what is the number of true positives? For accuracy, you need to know the number of true positives, right? Okay. What is the number of true negatives? I think eight, right? So true negatives is this region, right? So this region, like uh, the hollow circles in the light gray area. So these are not spam. The hollow circles are not spam, and they have truly classified as not spam. So I think there are eight hollow circles in the not spam region. Right. What is the false positives? So false positives are, spam. Uh, so if you see from this, so false positives are not spam, but are classified as spam. So these are the in the red shaded areas. So I think there are one, two, three, four, five, six, seven, 7 points. And false negatives are the whose true class is positive but are rated as negative. So these are the regions, the solid circles in the dark gray region. So one, two, three, four, five, 5 points. Right. So from here you can calculate the accuracy as 6 plus 8 true positive plus true negative divided by total, which would be 6 plus 8 plus 7 plus 5 total. Right. Did anybody understand that? How much is it coming out? So 8 plus 6, 4 into 26. Yeah. How much is it in percentage? It's yeah, 53%, 0.53. Right. Okay. So now, I guess now you guys have understood what are true positives, true negatives, false positives, false negatives, and all those things. And okay, someone is asking, not able to join the class. How can I get the recording? Yeah. Uh, Someone has shared the YouTube link. Yes. Let me check if there are any questions on YouTube. Sorry? Yeah, about the exam, I'm not sure. Probably NPTEL will inform you. Maybe you can check the mail. Yeah, I'm not in charge of the exam. So, okay. Okay. So you have been looking at, the assignments, right? The assignments you have got, right? Yeah. So it will be on the, yeah, it will be same as the level of the assignments. Also, you guys must have got previous year's question paper. No? No? Okay, I will check, and from the next class, maybe I will, um, give you some questions based on the previous year's assignment, previous year's question paper, and yeah, assignment as well. So I think I saw the week one assignment. I think it's basically the basics. I think most of which I have covered, and probably I think in one of the questions they have asked to calculate what is precision and what is recall and those things. So I think assignments. I think you are good with the assignments, right? About the main exam, I will just let you know. Okay. Okay. Someone has asked, can you provide one more example of classification? Right. So, yeah, like as in, fraud detection, let's say. So you have, so there is a transaction on your bank account, let's say, and you want to determine whether that transaction is fraud or not. So the bank on its end runs a ML algorithm, and if it's a fraud, it will get tagged as one, and in that case, the bank will stop the transaction. And if it's a not a fraud, then it will be tagged as zero. In that case, the bank will let the transaction go through, right? So yeah, that is another example of classification, and yeah. Yeah, so quickly, we don't have much time. I'll just go into precision and recall. So someone has asked what is precision and recall. So this is basically the definition of precision and recall: true positive divided by true positive plus false positives. Okay. So if you see from here, so this is the true positives and divided by the total predicted positives. Recall is true positive divided by true positive plus false negatives. So in this column, so true positive divided by true positive plus false negatives. So this is the uh, you know uh, definition of precision and recall. And well, there is something called F1 score, which is twice precision into recall divided by precision plus recall. So why do we need these three things? Precision, recall, and F1 score, and all those things. Why do we need these things? So let's say, you are predicting something. Let's say you are, predicting whether a person has cancer or not. Let's say based on the symptoms. Now, you don't want to miss out a person, right? You don't want to, let's say, if someone has cancer, he needs to be treated immediately, right? You cannot miss out. So you cannot afford to have, false negatives. So that means truly he is positive, but you are categorizing him as a negative. So that person will not receive the treatment, and that will be a very bad thing that could happen. So in that case, you try to minimize your false negatives, right? You can, if someone is, um, or if someone is negative but is getting tagged as positive, then it's okay. He'll get the treatment, and assuming that the treatment is not very harmful to a non-cancerous person, it's okay if even if he gets the treatment, right? But you cannot afford to have false negatives. In that case, you are classifying him as negative, although he has cancer, and he will not get the treatment. So that will be very bad. So in that case, what you will do is you try to minimize false negatives, and to minimize false negatives. So if you see in the recall, formula, in the denominator you have false negatives. So if you minimize false negatives, your recall will be very high. So in that case, you will not look at accuracy. You will not look at how accurately you are predicting, uh, you know, cancer or not. In that case, you will try to maximize your recall. So accuracy is not always a good parameter. So the moral of this thing is that even if you are like, accurately predicting, let's say your accuracy is 90%, your accuracy of the model, but still you are, not capturing all the people who have cancer. That could be have negative effect on, those people. So in that case, you'll not look at accuracy, you'll look at recall. So do you understand? Like these formulas are okay. You can calculate recall, you can calculate what is the percentage and all those things. But do you understand the, why we need it? The physical reason behind it, and why it depends on, uh, the right, on the problem statement that you are dealing with, right? So you cannot just blindly, maximize accuracy or maximize recall and maximize precision, you know. So in that case, you have to like think about the problem statement, what you want to do, and proceed accordingly. Right? So, any questions on this? Let me see. No, precision and recall is not the same, because in precision you have in the denominator true positive plus false positives, whereas in recall you have true positive plus false negatives. Okay, so they are not the same. Right. Someone has Pritham has given the formula. Precision is probability of actually positive given the positive result. Right. And recall is probability of correct classification as positive given it is actually positive. Yeah. Someone has raised a hand. Rona, please. Yeah. So you mean by the formula or by the physical significance? You mean? Okay. So by the formula, if you see, precision is, true positive divided by all the predicted positive. Okay. So whatever you are correctly predicting as positive divided by what anything you are predicting as positive divided by the total positive, right? So it is the probability that, the algorithm is predicting actually as positive given a positive result, right? As Pritham has mentioned. So given that you getting your algorithm is predicting a positive result, what is the probability that uh, those people are actually positive? Whereas recall is, given that they are positive, they have cancer. What is the probability that you are correctly classifying them as having cancer? So do you understand the subtle difference? In one case, you are given that they are actually positive. Another case, you are given that you are predicting as positive. So that is the difference. Yeah, please. Any other questions? Yeah. So that is a good question. Like how to increase the accuracy. So in the machine learning algorithm, if you like simply minimize the error, it will increase the accuracy. So like we saw in linear regression, right? So we are just fitting different lines, and we're choosing the line which is minimizing the error. So minimizing error just means maximizing your accuracy, right? That's what you want. But as I said, precision recall has its own importance. Where in there will be cases like as I described as a patient having cancer, there will be cases when you don't want to look for accuracy. I mean, you might have a model which has very low accuracy, but it has a higher recall. That would give you a more social impact or more, that will help those cancerous patients. So always, maximizing accuracy is not the right way to go. Sometimes you have to maximize recall, and in other times you have to maximize precision. So I'll not tell like in which cases you have to maximize precision. You guys think about it, and I mean, as I said in the case of cancer, you want to maximize recall, and you guys think about in which cases, in which practical cases you want to maximize precision. So I will not go into this graph. Maybe if someone has questions, we can discuss it later, but this is a graph where you choose how to which parameter to choose such that you get a balanced between precision and recall you know so yeah, this is a more advanced stuff, and maybe when we do logistic regression I can explain, or if someone has some questions we can talk about it. But yeah, so F1 score is something which balances precision and recall. So if you see, it is a product of precision and recall divided by precision plus recall. So if you have a higher F1 score, that means that neither your precision is too high, recall is too low, or and neither is the case that your recall is too high, precision is too low. So it achieves a balance between precision and recall. So there would be algorithms where you want to maximize your F1 score and find a balance between precision and recall, and whichever algorithm has a best F1 score, you will choose that as your best model. Right. So there could be cases like that. Again, if I get time, I will come back to this. In the meantime, I will just quickly go through this slide. So this is an example of clustering where you have data, unlabeled data, and by visualization, as I said, you can already see. But again, as I was telling earlier, that if you have a higher dimensional data, you cannot visualize. In that case, you need some clustering algorithms. Here, k-means, which again I think will be covered in the upcoming lectures. And this is what you get: three clusters after, mm, you know, after applying k-means clustering, right? So, okay, coming to the last slide. Okay, this is, I think, this is one of the topics where many people face issue. I'll just quickly explain through the slide and then I will take questions. Uh, and okay, so I think it has been covered in the lecture, right? So bias and variance. So one way I like to think about it, and I think you might find it easier if you think about it as well, is that bias is underfitting, variance is overfitting. Simply, So for example, you know, let me go to my notepad. Okay. So for example, if you have this data, right? This is your y parameter, this is your x parameter. Okay. So from looking by visual inspection, you can see that a quadratic curve will fit this, you know, very well, like this yellow curve, right? But let's say you are fitting a straight line, a linear curve, a plus bx. In that case, you are underfitting, right? On the other hand, if you are using, let's say some higher degree polynomial, right? Okay, let's say fourth order polynomial. Yeah. A plus b x plus c x squared plus d x cubed plus e x to the 4. Okay. So the fourth order polynomial you are fitting. So what you're doing is that you're overfitting the data. So this data might do well on your training set, but this will definitely fail on your test set when you're testing the data ultimately. Whereas in this curve, it is already underfitting. It is also bound to fail in your test data. So both of this will have high errors, you know. But this is the case where which we call bias, and this is the case which we call variance. As I said, easy way to remember: bias is underfitting, variance is overfitting, right? So if you see, this is your training set. So variance, if you see, will have almost negligible error in your training set, right? But in the validation set or in the test set, it will have uh, higher error because it is overfitting the data. But your test set might not represent the training set, right? Test set might be little bit different. Although your algorithm is perfectly fitting the training set, it will not fit the test set. So that is where variance comes from. So one feature of variance is that low training error but high test error. On the other hand, bias has both high training and test error. Okay. So that is the mainly the difference. Again, now I'll come back to my slide. Okay. So if you see, so this case, you have both. So I think the red line is the in this graph. The red line is the uh, test error, whereas the dotted line is the training error. Whereas the yeah. So in this case, both are high. The test and the training both are high. So you get bias because your model is being overfitted. Whereas in this case, variance, your uh, your test error is high, but training error is a little bit low. Right? It starts from low, but as you increase the model complexity, it will get higher. Right? Okay. So yeah. So the best way to go is find an optimal region where you get both cross validation error low and your training error as low as well. Right? So here is again one more graph. If you see, so this is the case of high variance, whereas overfitting, the right top graph. So you see that this is the error we are calculating. As I said, the training error will be high, but as you increase the training set size, the training error will become higher because you're like overfitting the model, right? You're overfitting the model, but at the end, if you increase more and more, training examples. So let's say this is a one-dimensional data. If you add more features and add more training set, your error is going to go high because you're already overfitting and you'll not be able to fit the extra data points that you are getting, right? So that's why training error will rise. And again, this is the test error in green, which will decrease. And you see this gap, right? So this is the gap that we'll observe in variance. Compared to bias, when you are underfitting data, you will not observe this gap. So error will again both increase, but you will not observe this gap. So right now, so the main question we should ask is that how to reduce variance and bias both, right? So variance, if you see, we can reduce by increasing the training set size. So if you extrapolate these two lines, you know, your test error and training error will go towards the desired performance, and your both errors will diminish. And sorry, the test error will diminish, and you will go towards the desired performance by increasing the training set size. How to reduce bias? You see this both the training error and test error are high compared to the desired performance, as I showed you from my notes, right? So how to reduce bias? There could be many ways. One of the ways is like increase the number of features. So as you saw that our model was underfitting in case of when we use a linear model, right? So if you see in this graph, we're using a linear model, right? So this one. So this is a linear model. So what we do, we can increase and add more complexity. Let's say we can increase cx square, and in that case, we'll fit the graph uh, correctly, right? So that these are the two ways which you can reduce, bias and variance as well. So I guess I explained it in a hurry. So can you, I mean, if you have any questions, please ask. And I think this is the last slide, and I have some. Yeah. If you don't have any questions, then these are some of the questions that you can, note down and think about at home, and come up with answers. It will be interesting for you as well. Okay, someone has asked how to reduce bias and variance. So as I said, to reduce bias, you increase the number of features, right? So in my notepad, so here you are fitting you're underfitting. So you're fitting a linear line, a plus bx earlier. Now what you do is you increase the feature. So if I increase a second order polynomial, then we are reducing bias. We are fitting the graph exactly, and this will have lower training error and lower test error as well. And to reduce variance, as we saw, like we can increase the number of data points. So basically we can get more points, we can collect more points, and then we can train our model again, and this will, you know uh, if you can see, this will better fit our training data and as well as test data. So variance increase, get more training data, and bias, increase the number of features. And well, there are some other ways also you can like reduce variance, like regularization and all those things. I don't want to go into the details, but if any of you know regularization, please, you can pitch in. And yeah, I guess it will be covered in upcoming lectures as well. So yeah, but yeah, right. So you see, like as I told you, like let's take the example of the housing prices. So here you have like your data contains like let's say 10 features, right? Number of rooms, size of the house, location of the house, and so on. So now, uh, will you use all the data, all the features that you have in your hand, right? So that is the question. Like, is if you're, let's say, if you have built your initial model based on number of rooms, now you want to add another feature. Let's say the size of the house. Like you want to see like whether that size of the house, that feature is providing additional input. If that is reducing the error, if that is producing better performance to your system, to your model, then you will add that feature, right? Otherwise, you will not. So there are like lot of algorithms, like for example, forward propagation, backward propagation, in which you can select your features. So forward propagation is just was the example that I was showing, right? You start with one feature and then you add another feature and see whether that is providing additional input to your additional, whether it is improving your performance, whether that is providing any additional insight into your data, into your housing price, that is what you want to predict, and then you select that feature, otherwise you don't. And then you do it for n number of features. That's how you do it, and that is the forward propagation. You're propagating forward, and you're selecting features as you propagate forward. On the other hand, backward propagation is when you have like you start with the whole feature that you have at your disposal, and then you remove one feature, one by one feature, depending on whether it is improving your performance or not. And then you finally end up with the feature, and that is what the feature that you're going to use in your model. So that is the basically the feature selection. Is that clear? Yeah, I will share YouTube link, PPT, and notes. Uh, don't worry about those things. About the deadline of the assignment, please check in the course website or the email. I'm not sure. I'm not sure about the date, but I'm sure they have mentioned it. And any other questions? And about references, yeah, let's get it, like, yeah, sorry. Yeah, let me just tell about references. So about the references, so today this was just an introductory lecture, so I didn't go deep into any particular algorithm. So when I go into some algorithm, I will just cite the sources for that algorithm. So this is just a general introduction. If Yeah, again, yeah. So someone is asking something, please. Right, right. So right. So you see, like, you have your data, right? And like like from this like you have n-dimensional data which you cannot visualize, so you don't know. Let's take the example of linear regression. So you don't know whether a linear plot will fit your model, or a quadratic plot will fit your plot model, or your sorry, quadratic plot will fit your training data, or a cubic plot will fit your data, and so on. You don't know, right? So what you do is that you divide your total data into training and cross validation part. Now, what you do is that cross validation is important in hyperparameter tuning. So, if you are looking at this word, tune hyperparameters, right? So, this is the part. So, I didn't mention, I didn't tell earlier, like, what does it actually mean? So, it means that you don't know, like, which whether a linear, quadratic, cubic plot, which will fit your data the best. So that is how you tune, right, using cross validation. So you train your model using linear first, and then you check the error on your cross validation, and then again you do train your model using quadratic, test it in cross validation, train with cubic, test it in cross validation, and so on. And then you decide, like, which is giving you the lowest cross validation error, and that is the model that is going to probably fit your data the best, because you cannot judge your judge on the basis of your training data error, because that is the data on which you're training. And as I saw that, if you're looking just at the training error, you might end up overfitting that, because the overfitted graph will give you the least error, whereas you don't want to overfit. So that's why you don't look at the training error, you look at the cross validation error. So that is where the cross validation comes in, right? And that's how you tune hyperparameters. So what is the use of cross validation? Tuning hyperparameters. Okay. So that is the thing. Is that clear? Okay, someone is asking for question slide. Yeah. Yeah, sorry, go ahead. Okay. So yeah, another question I might add is that, come up with an example where you think precision is important, right? As I was talking about it when, I was explaining recall. So I gave you an example where you need to look at recall, not at accuracy. And you need to think about an example where precision is important and not accuracy and not recall as well. And again, how do you choose the optimal number of clusters? Yeah, I couldn't cover the example 3 in detail, but here you see level data. Here by I, you can see that, you can have 3 clusters. But what about 2 clusters? We can have this cluster as one, and this is another cluster. So how to determine what is the optimal number of clusters? We can do two clusters here as well, clusters here as well. And what is the optimal number of clusters and how to decide that? That is the question. And what algorithms can be used for a spam classifier? Again, so one is logistic regression, as I was saying, and what other algorithms can be used as a spam classifier? No? Maybe this is a you know, you don't have to, go into detail of each algorithm, but, think about, like, if you know any other algorithms, you think about whether that can be used as a spam classifier or not. And yeah, another question is how to calculate precision and recall when you have more than two categories. So, yeah. So basically, right now we saw that you have only two categories, right? You have only spam or not spam. What about you have like many more categories, like let's say animals, as I said, like you can have cat, dog, horse, cow, four categories, let's say. And then how do you calculate precision? How do you calculate recall? How do you calculate true positives, which are true positives, which are true negatives, and those things? And yeah, these are the questions you need to think about. Maybe Google a bit, and you can, you know, get the answers. And if not, we can discuss in the next lecture, maybe. So yeah, every Tuesday we'll meet from 7 to 9. And yeah, if you have any other questions uh, before wrapping up, please let me know. Yeah, assignment due date, I'm not sure. Like, I don't said by the professor herself, and talk to her about that. Yeah, someone has raised hand, please. Yes, 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 yes. You'll get the videos and the slides. And I'm sorry if some of you couldn't join, and uh, I'll take some questions. So you watch these videos. So those who are not able to start, watch the video and the slide and the notes, and you can ask me questions later. So yeah, going to get, so as I think I have shared the uh, chat in the YouTube. Okay, wait a minute. Okay, so one thing I would do is that I have shared the my YouTube channel. Uh, Let me share it again. Okay, and there you can find the YouTube video. Okay, I will do one more thing. Uh, you check out the my channel, and I have also mentioned in the link of the video. So if you go into the channel, you can find the video as well very easily. And PPT you can get from NPTEL as well. And I will do one more thing. I will attach the PPT in my YouTube description, or in the comments. I'll attach the PPT there as well. And you can also get it from NPTEL. Either way, I will attach it actually. Yeah, so you can easily get it from there as well. Is that fine? Yeah, and yeah, sorry for the if some of you are not able to join. So you go through the video, check the PPT and everything, and you're gonna ask me questions at the start of the lecture next week. I'll take up questions for some time, and then I will start with the PPT for the next week. Any other questions? Yeah, someone is Niryogi Narasimhan. Okay. Eh, yeah. So yeah, I'm not sure about the exam pattern. So Uh, I think I will discuss it in the next. This is a task for me that I will see what is the exam uh, pattern. I mean, I can tell you about the last year's pattern, but I'm hoping that it will be same this year. But yeah, but you will be more be able to inform. You will be informed about it from the NPTEL part, because the exams and pattern, those things are, I don't set those exams and or assignments. So those are set by the professor and the regular TS. But I can check with the uh, previous assignment and previous year's paper, and then I can give you an idea like how difficult are the questions and what are the type of questions. But I cannot comment on this year's pattern or difficulty level. I'm hoping that it will stay the same. Yeah, yeah. I will discuss the problems from previous year's papers as well, previous year papers and assignment. I will discuss them. Yeah. Yeah, so I will look into that. And if you're not able to join Google Meet, you can join my YouTube live. This will be same next week as well. I will run a YouTube live as well next week, and you can join there, and you can ask questions in the YouTube chat as well. So I will suggest that maybe people who want to ask questions orally, they can join Meet, and if you want to ask questions on chat, you can join YouTube live. So I think that will be convenient for everybody. And otherwise, I will also look into uh, the number of participants. Okay. Yeah. Yes, it is fixed. Yeah, today I ran a bit longer, but yeah, I will try to keep it because it gets boring after 2 hours. So yeah, I'll try to keep it to the time. So yeah, if there are no questions, we can wrap it up, and maybe I can take questions on this today's lecture at the start of the next week. Okay. Okay. So yeah. Yes, the Gmeet link will be sent, and the YouTube link you can get from my channel, right? You can yeah. If you open my channel, it will come up. So I will end the call, and